Now, proceeding from the previous lecture where we talked about the phase velocity, now let's go into the domain of grip velocity of these de Broglie matter waves, and and try to show that this de Broglie matter wave has a velocity equal to that of the velocity of a moving particle. So, so to start with this title, now, what is group velocity? How can we define it in some precise way? Suppose we have a group that consists of number of waves of different frequencies, and and these waves are superimposed on each other, right? For example, let's take a white light. White light does? It has white light. It has a range of frequencies present in it, from 3,000 angstrom to 7,000 angstrom, right? And uh, and this the velocity with which this slowly varying envelope. So there we have an envelope of different frequencies in white light, and to define the group velocity here is it's basically the velocity with which this slowly varying envelope of the modulated pattern of these waves. This modulated pattern of waves is due to a group of waves traveling in the medium, and this velocity is referred as the group velocity. And the importance of group velocity lies in the fact that this is the velocity with which the energy in the wave group is transmitted. Now, to have the expression for group velocity of de Broglie matter waves, let us assume that we have two waves, say y1 has amplitude a cos omega 1t minus k1x. Now this is the, 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 the displacement of a wave given by y1, where a is the amplitude of the wave, omega is the angular frequency, and k is the propagation vector. And if we choose another wave of same amplitude with slightly different frequency, omega t minus k2 x. Okay, if we choose these two equations and apply the superposition principle on these two waves, we will have what we will have is the resultant of these two waves. So if I assume that resultant is y, and that will be y1 plus y2. That's clear to everybody. Everybody understands it. And and if I go back to the definition of phase velocity, what was it? It was c square by v, and we could write it in terms of omega and k. This vp is also equal to omega by k, and we can evaluate this thing from this equation itself, right? So this phase velocity is omega by k, where omega is the angular frequency and k is the propagation vector. Now, if we dissolve this, for omega we have 2 pi nu, for k we have 2 pi by lambda. This 2 pi and 2 pi can be cancelled, and we will have the velocity that is nu by lambda. Yeah, so this lambda will go up, so nu lambda, this will give us the phase velocity. Now the point is that what we assume in this case is that the ratio between omega 1 and k1, which is indicative of the phase velocity, uh, omega 1 by k1 and omega 2 by k2, and omega being equal to 2 pi nu and k being equal to 2 pi by lambda. Now, what is further noted here is that this ratio between omega 1 by k1 is not equal to omega 2 by k2. Right now, so what does it mean by assuming that the two ratios are not equal? We are making sure that the medium is dispersive. So we have a dispersive medium here. So in order to move further from this point, now to calculate this y will be, a will be out, and what we will have is cos omega 1 t minus k1x plus cos omega 2 t minus k2x. So this will be the result of applying the superposition principle at this stage. So we can make use of because we have a situation like cos p plus cos q, and we can use the formula of cos p plus cos q in this case, and what we will have is we will get 2a cos of when we make the plus. So in that case, omega 1 plus omega 2 can be written here times t by 2 and minus k's. The k's will be also added, so minus will be out there. Then this will be k1 plus k2 divide by 2. So this is my into x. So this is my cos. This is p plus q, and another term will be in terms of the subtraction. So in that case, we will have omega 1 minus omega 2 divide by 2 times t minus k1 minus k2 divide by 2 times x. So this will be the result that we will get by making use of the formula, that's cos p plus cos q. Now if I write down this equation in a very short form, this will be 2a cos, and here I will use omega t minus kx, and here I will use cos del omega by 2t minus del k by 2x. Okay, I can write like this. All I have done is that this omega, I have taken this omega as the average of omega 1 plus omega 2 by 2, and I have taken this k as k1 plus k2 by 2, and I have taken this delta omega as omega 1 minus omega 2 by 2, and I have taken this delta k as k1 minus k2 by 2. So this should be clear. So what we have here in this equation is we have this equation made of two parts, and this is one part, and this is another part. Now, what we are trying to do here is to obtain an expression for this for the group velocity that we have. Now, if we go back here in terms of this omega and k, here we can easily find that this for case 1, I will have what I will have is phase velocity that will be simply omega by k, and omega is known to be as 2 pi nu, and k is 2 pi by lambda. So this will be nu lambda, right? So this is the ordinary phase velocity that's linked with the result of these two waves. But in addition to this, we have a second wave. We have another wave whose frequency is if I write here, whose frequency is delta omega by 2. And this group of waves are traveling. They have a propagation vector. They have a propagation constant. Equal to delta k by 2. All right. So what we have is we have a modulated wave, and we can represent that in some geometrical form where we have the modulation of the waves. Now the point here is that this thing is that it consists of a group of waves of the first type, and is very slowly moving envelope of frequency delta omega by 2 and propagation constant delta k by 2. Now this modulated pattern moves with the velocity. This modulated group of waves moves with the velocity known as group velocity, and that will be delta omega by delta k, right? And this delta omega by delta k is called as group velocity. Now if we choose this delta omega and delta k very small, if we choose them extremely small, in that case we can write down the group velocity is d omega by dk. Right now, if we break down this omega, this is d of 2 pi nu by d of k. For k, we have 2 pi by lambda. So what we will obtain is the group velocity will come out to be 2 pi, this 2 pi and 2 pi, they will die. So what we will have here is we will have if we write down this equation here, so the differentiation of 1 by lambda, that will be minus lambda square times nu by d lambda. So because we better understand that if we have differentiation of 1 by x, that is minus 1 by x square dx. So this is what has been used here. So this is giving us the measure of group velocity as lambda square dou nu by dou lambda. Now proceeding from here with an intention to obtain the relation between this group velocity and phase velocity. So let's move on from here to obtain that relation. Now what should we do here is if I start with the phase, the definition of phase velocity is omega by k. So what does it mean? It means that omega is simply k vp. It's k times phase velocity. Now what's our group velocity defined as? This is defined as the derivative of omega with respect to k for very small values of delta omega and delta k. So what can I do here is, instead of using omega, I will use k vp divide by dk. My intention is basically to obtain a relation between the phase velocity and group velocity. Now what's going to happen here is that we have this vg. Okay, we have this vg now equal to differentiation of this k and vp. Okay, so and in the denominator, what we have here is dk, and this we can obtain as vp plus k dvp by dk using the UV rule for k and vp. So this is it, and then what we can have, what we can have more than this is that this group velocity, this has been already evaluated in the previous case as as having a value, and as having a value in terms of the phase velocity. So this Vg will be Vp. If I choose something here like k, if I take k, what's k? That's 2 pi by lambda. And if I had to calculate dk, what will be that? That will be minus 2 pi by lambda squared. That should be the case. That should be absolutely the case. And from this we have k and we have dk, and we can use this dk in this equation, right? If we use this dk in this equation, what we are going to get is Vg is equal to Vp minus, there certainly will be the cancellation because we have k here outside, okay, and this k can take its value, and what we will obtain from here, there will be cancellation of lambda and lambda. You can do it in a very, very trivial way, and we will get minus lambda dvp by d lambda. So this equation is giving us the relation between group velocity and phase velocity. The thing should be clear up to now. Very simple. Now the final aim of this presentation is this discussion is to see that the group velocity that we have calculated, and we would like to see that this group velocity, what is its velocity, and that velocity should come out to be equal to the velocity of the particle itself. So that means now the group of waves is associated with the particle. So in order to obtain that relation, what should I do is that, as I understand that a particle moving with the velocity v is supposed to consist of a group of waves. Now, according to the de Broglie, as we were discussing till now. So for a material particle of rest mass m naught, we can and having total energy E, we can write its energy equal to mc square, and replacing this m by the relativistic mass, that is m naught by under root of 1 minus v square by c square. All right, this should be the case. So E will be times c square here. This will be the energy. And what about momentum? And momentum is what? It is mv, right? So this is m naught by under root of 1 minus v square by c square, and here I have v. All right, so I have energy and I have momentum, and if I have these two, I can calculate the frequency. So what will be the frequency? That frequency will be E by h. Right now, what is h? H is the Planck's constant. So this will be equal to 1 by h times, for it is m naught c square by 1 minus v square by c square whole raised power 1 by 2. Now this is the frequency. Now if I want to convert this frequency into angular frequency, all I have to do is to multiply it by 2 pi nu. So this nu will become omega, and here I will have 1 by h, then I will have 2 pi m naught c square by 1 minus v square by c square. This should be the case. Now, if I differentiate this equation, if I calculate its d omega, I want to calculate its d omega. So what will be the d omega in this case? So d omega. Okay, so all I have to do is to write down 2 pi m naught c square by h. Okay, I would like to take it up. This is 1 minus v square by c square whole raised power minus 1 by 2. Okay, so this should be the case, and so what will be d nu once you differentiate this? What we are gonna get out of it is it will be 2 pi m naught c square by h. Yeah, that should be the case here, and then what we are going to obtain is we will take its derivative, minus 1 by 2 will come down, and what we will obtain here is I have taken it up. Okay, so I have taken it up, so this is minus, so this will be minus 1 by 2 times 1 minus v square by c square whole raised power minus 1 by 2 minus 1. Now this should be the case here, right? So what am I going to get after this is 2 pi m naught c square by h, right? So here I have not written down the internal derivative of this minus v square by c square, so that will be minus 2v by c square. That should be the finality of it. Then this minus and minus will become plus. This 2 and 2 is gonna cancel, and what we have here is v. Okay, this v will come out. Okay, it's outside this, and by c square is out, and inside what we have is 1 minus v square by c square whole raised power minus 3 by 2. So from here we could see this c square and c square will cancel. So what we get, 2 pi m naught by h divide by 1 minus v square by c square. So this is d omega. V is also here. Okay, this v is also here. Now this is what we have is d omega, and here if we go with lambda now, I mean if I start with lambda, so I will call this as equation 1 for the time being, and let me go with, my aim is basically to find the velocity, the group velocity, and I want to correlate it. I want to find this group velocity, its relation with the particle velocity. So 7 is here. Now here I would like to have de Broglie equation is h by p, as we have already written down this p, and what we have is h times 1 minus v square by c square whole raised power 1 by 2. So this is divided by m naught v. So from here, this is my lambda, so what will be my k? My k is basically 2 pi by lambda, so that will be reverse of it. So this will be, so here this will be 2 pi, this m naught v, it will stay in the numerator, and divide by h times 1 minus v square by c square. So this is k, but what I have to find is dk. As we found d omega in the previous case, and we found that equal to this thing that we have obtained here. Now what we want is, we want to we want to do the differentiation here and obtain the result. So what we have here is, we can understand here it should be 1 by 2, and we have here k. So on differentiating it, I will have dk. So what will be outside will be 2 pi. 2 pi will be outside, and m naught will be outside, h will be outside, and inside I will have v, and I will have 1 minus v square by c square whole to the power of minus 1 by 2. So this thing will act as uv rule, and this whole thing will act as v. So we would like to differentiate this, and what's going to happen here is okay, so dk will be 2 pi m naught by h times, right? And so what we are going to do, suppose this is suppose I will take this as u and this as v, so this will be 1 minus v square by c square whole minus 1 by 2, and dv simply plus, now this v will remain as it's. I think we should go for the next page. All right, so what we have here, so we have dk equal to 2 pi m naught by h. So what we have here is 1 minus v square by c square raised power minus 1 by 2 dv plus v as its. Now the differentiation of this, so what will be that? That will be minus 1 by 2 times 1 minus v square by c square whole raised power minus 1 by 2 minus 1 will give us minus 3 by 2, and then the internal derivative of this v square by c square will give us minus 2v by c square, and this should be the case. So from here we should move, and we should look for where is the first page where we have got d omega. Where is d omega? D omega is here. Okay, now moving on from here, what we will have is we have 2 pi m naught by h. All right, and we can see here this is 1 minus v square by c square dv, right? And plus this minus and minus will turn into plus. This 2 and 2 is going to cancel, and this v and v will make it will make v square. So I can think of getting something common out of these two, and what that something is, I would like to take 1 minus v square by c square whole raised power minus 3 by 2. I will get it out. Now if I will get it out, so what should I multiply so that I get raised power? I will get something raised power minus 1 by 2. I should multiply it by 1 minus v square by c square. Okay, if you multiply the two, you will get raised power minus 1 by 2, and from here we have already got this minus 3 by 2 out. So what is inside here is plus v times v will give us v square by c square. So let me close this. So what we have dk equals 2 pi m naught by h. Okay, so here we have 1 minus v square by c square whole raised power 3 by 2, and here this v square by c square and v square by c square will cancel. This is minus, right? So we have dk now. What is dk? It is like 2 pi m naught by h times 1 minus v square by c square whole raised power 3 by 2. Now what was dk that was obtained? This is dk. What was d omega? This is my equation number 2, right? So I would like to calculate this group velocity. So, so what is group velocity is what is group velocity is defined as it's defined as d omega by dk, and we have calculated here d omega is, what is it? It is 2 pi m naught v by h times 1 minus v square by c square whole raised power 3 by 2, whole raised power 3 by 2. So divide by dk. So dk जो है what we have here is we will take the reciprocal. So this will be 1 minus v square by c square whole raised power 3 by 2 divided by 2 pi m naught. So this 2 pi m naught will go. This whole thing will this whole thing will go. So h must be here. This h and h will go. This thing will go. So this Vg will come out to V. Now see, what we have concluded here is that as we can say that the de Broglie wave group that's associated with the particle, it travels with the same velocity as that of particle itself. So the case is not the case that was augmented in case of phase velocity, where it could have seen that the wave was away from the particle. And here what we see that the group of waves that we have, they are associated with the particle itself, and the velocity with which the particle is moving with the same velocity, the group of waves that are traveling with this particle, they are moving with the same velocity.